but just forward facing. I'm not videoing you something released on. So let's just take a shot there actually. Can't go too far. 1 minute, okay. So this is the rays through the telescope, and what I'd like to do is go through the angular magnification of the telescope and then relate that to the measurements you took when you built that telescope on Friday. Magnification normally, and what you'd associate with is what's referred to as linear magnification, and that's the height of the image over the height of the object. So the magnification is making the image appear bigger than the object. It's not relevant with astronomical telescopes because the things we're looking at are generally very small, so it doesn't make a lot of sense. So instead of using those two ratios, they use something called angular magnification. Okay, and the angular magnification M is defined as, I'll give you the definition and I'll explain it, angle subtended by image. Now I was going to check on here whether it's, because it's a long readed thing, image and I. Divided by angle subtended by object at unaided eye. So it's a bit of a mouthful, although if you look at the formula sheet, that's what it is. Because it's a ratio of angles, there aren't any units. So it's just a ratio. No units, as simply a ratio. So what does this mean? Because it's quite a wordy thing. Angle subtended by image at eye, angle subtended by object at unaided eye. So if you remember what you did on Friday when you made that telescope, I asked you to make two measurements. One was the angle subtended by the image. So if that's the ruler, and that's the lens, and that was your eye looking at the lens, then I asked you to make two measurements. One was the distance from your eye to the lens, that one there, and one was to make an estimate of the height of the image in there. And of course what that allows you to do is, and what we will in a second, is to work out the angle subtended, created by the image. So that line there is the image, yeah, at the eye. Does that make sense? That's what that is. It's the angle subtended or created by the image at the eye. So what we've done, we've measured that distance and that distance, and we've got a right angle triangle, and we can work that angle out later. Okay, which I'll come back to in a second. The other one that we did was to just for the third person to walk in and not shut the door and so on. So this time you're measuring the distance from there to there and the distance from there to there. And again, the object is sort of there. Okay. So that was the distance, or the angle subtended by the object. So this is the object you're looking at way away by the unaided eye, just looking at it with your eye, and it would be this angle in here. So this is the angle subtended by the object at the unaided eye. There's no telescope there. To make life a bit easier, rather than writing all this stuff out in a second, we can arbitrarily call these angles. And the convention normally that this is referred to as alpha and that's referred to as beta. It just makes it easier for me when I'm talking rather than having to write all this stuff out. But that's what it is, and that's how it relates to the definition of these things. So I could also say this is just equal to alpha over beta. On the formula sheet, they don't use this, but they do use those in the textbook, the online textbook. Okay. So you measured those two things. You measured this distance, that distance, that distance. So you should be able to come up with an estimate for the angular magnification telescope, which we'll do in a moment. Okay. I just want to show you something else instead, and how you actually use that. Just coming back to the actual telescope itself, how do these angles relate to this actual telescope itself? Well, the angle subtended by the image, the angle created by the image, and this will be the image here, is actually that angle there. So that would correspond to alpha, the angle subtended or made by the image. So that is also alpha in there. You don't need to know this, I'm just showing you where these things come from. This distance from there to there is the focal length of the eyepiece. That distance from there to there is the focal length of the objective. The angle subtended by the object at the unaided eye, if you're looking at this without the telescope there, you would think, hold on, I'm going to say it's that angle there, and you can say, well, it's not really, because I'm looking at it here, and I'm taking the angle from there. So if we had a tree that I was looking at, and I had my eye, the angle subtended by the tree would really be that angle there. If I then stuck a telescope in me and said, well, that's my telescope that I'm looking at the tree with, because what I'm saying here is that the angle subtended this point here would be the angle subtended by the object at the unaided eye, which it isn't really, is it? Because, you know, it's here, not there. But normally we're looking at objects which are much, much further away, like light years, maybe hundreds of millions of kilometers. So the size of the telescope is negligible compared to the distance I'm looking at. So it's reasonable to say that this is the angle subtended by the object. So you have this angle beta in there. And what you've got are two right angle triangles. You've got a right angle triangle in there and a right angle triangle in there. And just using some simple SOHCAHTOA stuff, if this is the height of the image, I'll call it HI, height of the image, tan alpha opposite over adjacent. So tan alpha is opposite over adjacent, and tan beta is opposite over adjacent. So because the image height is the same in both cases, I can say that FE times that, FE tan alpha, bring that across, will be F naught tan beta, so that tan alpha over tan beta is F naught over FE. Now that looks a bit like that, except we've got tan alpha and tan beta rather than alpha and beta. However, when the angles are very small, the tan of alpha is more or less equal just to alpha. And it's the same thing for tan beta, obviously. So once you get small angles, tan of an angle just equals the angle. So in fact, the ratio of the focal lengths objective to eyepiece is the same as the ratio of these two angles, is actually what we call the angular magnification. So I've got another equation that you need to use. You don't really need to know this stuff here. You just need to know the relationship I'm going to give you now. So it can be shown that M equals F naught over FE, the ratio of those two focal lengths. And this is another one which is on the formula sheet. this little note in normal adjustment, distance between the two lenses equals f0 plus fe. Now I'm putting a blue box around that because it's not on the formula sheet or anything, but it is an equation you need to remember. Because what you can do is you can give people a magnification and the total distance between the two lenses, and then you get a pair of simultaneous equations to solve to find FO and FE. So any question you get using angular magnification will be a combination of these three equations here, and that's it. So you can't make it any harder than that really. The sort of hardest mathematical thing is to present students with a pair of simultaneous equations that they have to solve to work out FE and FO, and then possibly doing something around this as well. But they're the three sets of equations. There's nothing else. That's it. So I'll make sure you remember that, or write them down certainly, because that'll be the extent of any questions you get. What I want to do is show you this relationship with tan alpha and alpha and beta, and work out the magnification of the telescope that we had, and then I'll go through an example question about how you should structure any answering these sorts of questions. Really, when you're talking about angles subtended by things, when you're looking at them, really it's like that. I'm drawing them as right angled triangles, but really it should be more like an arc like that. And there's a relationship that the arc length of a circle, S equals R times theta. And when in radian. And when the angle is very small, I can approximate this curve to a straight line. That's the equivalent small angle approximation for tan alpha equals alpha. So strictly speaking, that is what we're doing. However, I use right angled triangles because that's what you're more familiar with, and it works just the same, where this would be S, that would be R, and that would be theta. So theta is opposite over adjacent. Tan of the angle opposite over adjacent. For small angles, tan of the angle is equal to the angle. And it's the same here, that theta equals S over R. So that's where it comes from. Yeah, but I present it like this purely because that's what you're more familiar with. Really, strictly speaking, it's that. And the implication of that is that the angles have to be in radian. Okay. So does someone have some data that they took from a telescope? So I want to show you why that's important. Any values for these two sets of things? Anyone? Have you got anything written down? Oh, come on, you're all there on Friday, weren't you? Oh, well, I'm not moving on until someone gives us some numbers. Tom, you got some numbers? Jack, you got any numbers?
Yeah, some.
This will be a lot faster if someone just say, I've got them and here they are. Meg, have you got any numbers? So you can use yours, but you're sure you got it wrong. Why are you sure you got it wrong?
I've got some here.
Hold on a second. It doesn't matter. Okay. Will then?
On the image one, the height in the lens was 4 centimetres.
That's big.
And height to lens was 5.5.
Alright, okay. 5. Anyway, yeah. And the distance from your eye to the lens, more or less?
5.5 centimetres.
Oh, 5.5,
yeah,
sorry.
That's correct.
And then this one?
from your eye to the ruler was 56 centimetres, and the other one was 3.2. 3.2.
Okay. So this is how you can work it out, right? The magnification is the angle of that over that. So I need to find those two angles. Because these are small, I mean, even this is a small angle, frankly, yeah? So what I'm going to do, I'm going to say that tan alpha just equals alpha, and that's opposite over adjacent, which is going to be 4 over 5.5. So 4 over 5.5 equals 4 divided by 5.5, 0.73 radian. So by doing that, it's in radian. I don't need to press inverse tan. You can if you want, it'll make no difference. You get exactly the same answer because it's small angles. Tan beta is just beta, opposite over adjacent, that's 3.2 over 56. Obviously these distances have to be in the same units. 3.2 divided by 56. Yeah. So therefore the magnification is that divided by that. So 0.73 divided by 0.057. And that 0.73 divided by 0.057. 12.8. We'll just call it 13. So on a linear telescope, then the image you look at will be 13 times bigger than the actual object itself as we're looking at it. Okay, with the telescope and then with the unaided eye. Well, let's work out what it should be. So we can use this to work out what it should have been. And the focal length of the objective was, anyone remember what it was?
50.
Yeah, well done. It's 50 centimetre. Put here. Someone on the ball. Eyepiece? 5. So the actual magnification of that telescope should have been f0 over fa, 50 over 5, same units again, 10. So hey, it's pretty close, well done. Okay, and that's it. Does anyone have any questions on that? Okay, well let me give you an example question. And in fact, these questions are reasonably straightforward, but they end up being complicated because of the words that are used in the question. And so I have a strategy of how to do these things that I would insist you follow. Of course, you don't have to if you don't want to, but then you're going to struggle to answer these questions, believe me. So, Galileo's first telescope had a magnification of 8. When he looked at a distant ship, the image of a mast, of the 20-meter mast subtended an angle of 16.0 times 10 to the minus 3 radian. Calculate how far the ship was away. So you have to try and put this into some sort of meaningful sense, because it looks like, well, I've got the distance of the ship, I've got an angle and a mast height and magnification. How does it all fit together? It's really hard to see your way through. I would always start these questions by drawing a pair of triangles. And it becomes very easy, honestly. So there's one angle, and then triangle, here is a triangle in there. And guess what these two triangles represent? This is the angle subtended by the object, so that's the object there, and this is the image here. And so the angle subtended or made by the object with the unaided eye would be that one, which I call beta, and the angle subtended or made by the image will be that one, which is alpha. And so I'll do that before I even look at the question, because a lot of the difficulty is interpreting what you've been given in the question and how it relates to this. But all of the question boils down to this. So I'm just going to put the information on, yeah? First up, okay, so it's got a magnification of 8, so M equals 8. He looks at a vision ship image of the 20-meter mast. Well, that's the object, and that means that's 20 meters. And he looked at the distant ship, the image subtended an angle of that. So which angle, this one or that one, corresponds to the 16? I should use the whiteboard solution at the moment, unfortunately. It's alpha. So the angle made by the image is 16. So this one here is 16 times 10 to the minus 3. So that's, I mean, in a sense, that's the hard part, trying to figure out which angle to be given. And then you need to say how far the ship is away. So I'm trying to find this distance here. And so you should see I've got triangles, yeah? So I'm trying to find this one. If I knew the angle, I could use the angle and this value to work that out. How do I get that angle? Well, I've been given this one and the magnification. And the magnification relates to the ratio of those two together. So I'm trying to find this angle, so I can work out D. I need to find the angle by using this angle and the magnification. So the magnification is given by alpha over beta. I'm trying to find beta, so beta is alpha over m. So that's going to be 16 times 0 times 10 to the minus 3 divided by 8, which is 2 times 10 to the minus 3 radian. And then small angle approximations, tan beta equals beta, opposite over adjacent. So we've got that beta equals 20 over D, yeah, angle opposite over adjacent. So D equals 20 over beta, which is 20 over 2.0 times 10 to the minus 3. 10, that's 10 times 10 to the 3, which is 10 kilometers. That's it. You can't make it any harder than that. No, seeing that. Yeah, you can't make it any harder than that. So the only thing you can do is to try and make it harder to work this out by giving focal lengths of the objective and eyepiece, and using those two other ones about magnification is f0 over fe. So I wouldn't give you that number. I'd give you the focal length of that and that. Yeah, and you've got to work that out yourself. Extra step. Or I'd give you the distance between the lenses and one of the lenses, and so you've got to use this equation. You know, if the distance between the two lenses was 2 meters, f0 plus fe, and I've given you the eyepiece distance, you need to use this to work that out, and then put that in there with that value to find that, and then use that to work out those ratios to put that together. I mean, that's what you can do. It's just 3 equations, that relationship, the two focal lengths added together is the distance between the two lenses. units. This has to be in the same unit as that. Yeah, but that's it. Okay, so it's actually relatively straightforward, even though it looks really complicated.